So once the probabilities for various events are known, there are some rules that we can use to speed up a bunch of computations. Like what's the probability something doesn't happen? Or what's the probability that two or more things of interest happen simultaneously? So this last section for Unit 1 talks about just basic rules of probability, things that every practitioner just needs to know to make computations a bit more streamlined, a little bit easier. And the first thing we should start out with are just the basic axioms about probabilities. Some notation, some stuff that's going to make writing down some of these rules a bit easier. And so we're going to call, just as a placeholder, some generic event that we're interested in by the letter A. So A is going to be our event of interest. It's going to be one or more outcomes in the sample space. And we're going to denote that sample space by just a capital letter S. So we might be interested in picking a random integer between 1 and 100. So S, the sample space, all the possible outcomes we might observe would be the integers 1 through 100. And A, our event of interest, could be any number of various things. A could be the event the picked value is a 4. Or A could be the event the picked value is less than 57, which is more than one outcome in that sample space. So here's some things you need to know about probabilities. Number one, since we're taking that frequentist definition, this one makes sense, probabilities have to be between 0 and 1. So if you're doing a computation, you get a negative value, a value that's bigger than 1, you know you've messed up somewhere along the way. Since the probability of some event is the fraction of time that that event occurs in the long run, well, of course, it's going to be between 0% and 100%. 0 is an impossible event. 1 would be it's always going to happen. Another axiom of probability is that the probability of obtaining an outcome in the sample space is 1. Makes sense. S is the set of all possible outcomes. You're going to get one of those outcomes when you conduct the experiment, so of course there's a 100% chance of getting one of the outcomes in that sample space. And the third axiom, and these three actually build up all of the rules we're about to introduce, talks about the probability of one or another event, or any set of what we refer to as disjoint events, events that cannot occur simultaneously. So we might be studying customer transaction behavior. Maybe event A1 is the event where a customer buys exactly one item in a particular purchase. A2 might be that the customer buys exactly 2 items. A3 would be exactly 3 items, etc., etc. A1, A2, A3 in this case would be disjoint events because when the customer makes a purchase, they're going to have exactly either 1 or 2 or 10 items in there. Well, when that's the case, when we're dealing with a set of disjoint outcomes, then we can ask, well, what's the probability that one or the other of these events occur? We can get that probability just by adding up the component probabilities in our question. So what's the probability that a customer makes between 1 and 4 purchases? Well, that would be the probability they make exactly 1 plus the probability they make exactly 2, exactly 3, exactly 4. You get the idea. And that's going to be very useful for us in business analytics because often when we are studying customers, we'd want to know, well, what's the probability they have 2 or more kids? What's the probability that they have 10 or fewer items in their checkout cart? Very often we're interested in numerous disjoint outcomes, and we're able to get those probabilities by adding those component probabilities together. Now, another very useful rule is the complement rule. If we know the probability that A occurs, the complement of A, the opposite of A, is going to be referring to the probability that A does not occur. So if the probability that I show up at a stoplight and it's green is 20%, I might be interested in asking, well, what's the probability of the opposite, that it's not green? The complement rule has us covered. Basically, it says the probability that an event does not occur is just 1 minus the probability that it does occur. So the probability that it is not going to be green is going to be 80% if the probability of it being green is 20%. Something's got to happen, either it is or it isn't, so those two probabilities are always going to be adding up to 100%. And there's a classic illustration in probability that relies on the complement rule to actually come up with an answer. Sometimes it's actually easier to calculate the complement, the opposite of the event that you're really interested in, because then getting the probability that you want is super easy. You just do 1 minus that probability of the complement. And so this problem is called the birthday problem. Essentially, we gather a whole bunch of random strangers into a room, and we ask the question, before conducting the experiment, what's going to be the probability that at least 2 people in the room share the same birthday? So we could have just 2 people sharing it. We could have 3 all sharing the same birthday. We could have various sets of people each sharing a birthday as well. We just have the very general question, what's the probability that at least 2 of the people in the room are going to be sharing the same birthday? Now, that's a hard question to actually tackle directly, just because there's so many different ways that at least 2 people can share the same birthday. We could have pairs, we could have triplets sharing the same birthdays, etc. And so in this case, the complement rule is useful because we can figure out the probability that all of the birthdays are unique in the room, and then do 1 minus that. The opposite of at least 2 people sharing the same birthday is no one shares a birthday. All the birthdays are unique. And so let's do that computation. The answer is always a bit surprising. And let's do a computation for a class of size 45 here. All right, so we're going to answer this birthday problem using the complement rule. So the probability that at least 2 people, there's my people right there, share the same birthday. That's a hard event to calculate because we might have multiple pairs of people, we might have triplets, etc. And so we're going to take the approach that, well, the opposite event is going to be easier. What's the probability that all birthdays are unique? And we'll take that probability, do 1 minus that, and get our answer from here. So I want to answer the question, what's the probability that all the birthdays in the room are unique? So what we're going to do, just to make our life a little bit easier, is to ignore the possibility that someone was born on February 29th. I've been teaching for over 10 years. I have yet to have a student actually born on February 29th. So this kind of making the problem easier by simplifying it is a pretty legit thing to do. So we're going to ignore those leap year babies, sorry to those of you who are, and we're going to go and calculate the probability that all the birthdays are unique. So how do we do this? Well, we're going to do some counting. So the probability that all birthdays are unique is going to be the number of sequences. Imagine we go through person number 1, 2, 3, 4, 5, 6, etc. It's the number of sequences where all the birthdays are different. So all different birthdays divided by the total number of possible sequences of birthdays that I might observe. All right, so our sample space are all possible sequences of asking basically people what their birthday is, 45 total people. That's a lot of sequences here. The fraction of that sample space that contains just the sequences where all the birthdays are different, that's the probability that we're after. So this denominator is particularly easy because if I want to know the total number of sequences that I can observe for these birthdays, well, that's basically the fundamental rule of counting coming in to help us out. So how many different possibilities are there? Well, the first person I ask has 365 birthdays to choose from. So does the second person. So does the third. So does the fourth. Each person in my entire sequence, each has one of 365 birthdays. So since this is like doing 45 different little mini experiments, each experiment being, hey, person, what's your birthday? That would be 365 raised to the 45th power. So I'm going to put a little 45, that's my little person, 45 people in the room here. So, all right, the denominator, easy to do. What about the number of sequences that are all different birthdays, unique birthdays? Well, same sort of thing. We'll use the fundamental rule of counting. In order for a sequence to have all different birthdays, well, the first person can have any one of the 365 days and still have that sequence be unique. The second person that we ask can only have 364 choices to avoid a duplication. The third person, 363, all the way down the line until we've gone through the 45 people in the room. So that would go down to 321 here. So, all right, the answer that we're seeking is going to be 1 minus, we're using that complement rule, the probability that they're all unique. So 1 minus 365 all the way down to 362, or 321, I don't know where 362 came from, divided by 365 raised to the 45th power. And if you throw that into R, what you would find is that it is a actually really quite big number. I'm going to throw it into R. You can't see it. Trust that I'm doing it. 1 minus the product of the numbers 365 down to 321 divided by 365 raised to the 45th power. That works out to be 94%. So pretty amazing, and actually on the homework, one of the questions I'll have you guys do is to update this number with a Monte Carlo simulation, routing a computer program, to take into account those freak leap year babies. And you'll find actually that the answer really doesn't change all that much. There's an additional slide in the notes that shows how that probability changes as you add in more and more and more people into the room. And once you get into about 25, 30 or so people, the chances actually come pretty good that at least 2 of those people will share the same birthday. Another useful rule for probability is called the addition rule. And this is going to help us out when we have the question, well, what's the probability that event A or event B occur? And there's something special about the word or in probability. When we say A or B, we mean at least one or both of those 2 events occurring. So we can imagine talking about what's the probability that a shopper, when they check out from Kroger, has apples or bananas. So apples or bananas in probability means just apples or just bananas or both of them. Essentially, at least one of those 2 things has occurred. So here's how we go about calculating this probability, the probability of A or B occurring. What we do is we add up the 2 component probabilities. So the probability that a customer has apples plus the probability they have bananas, and then we subtract off the probability of their intersection, the probability that both events occur. Now, why does this formula make sense? We can derive it visually if we just look at a Venn diagram. So if we imagine, say, that the entirety of the white space of the slide is our sample space, and we're going to pick, say, some point at random in the sample space, some point at random on this slide, well, we might land in A, we might land in B, we might land in A and B here, where A and B are both occurring, or we might land just completely outside of it. So since I know that the probability of some event is just the fraction of the sample space that contains that event, if I ask what's the probability of A or B, I can see that I can get to that area by adding up the area devoted to A to the area devoted to B, and then giving back the area where both occurs, because that would have been double counted when I added the area for A to the area added for B. So it makes sense. If you want to know the probability of A or B occurring, just add up those 2 component probabilities and subtract off the probability that they both occur, because you would have double counted that part when you summed up those 2 probabilities. So here's a good example. I don't know if you guys have been to In-N-Out. It's a great fast food burger place, mostly concentrated on the West Coast, and their menu is very, very simple. They basically just serve burgers, fries, and drinks. So let's imagine we're dealing with this case, this In-N-Out restaurant, and we know that the probability that a particular order has just a burger, or sorry, a burger in general, might have other stuff, is 70%. So 70% of orders in the long run tend to contain burgers. 60% of those orders have fries, and maybe something else. And we also know that 45% of orders have both burgers and fries. So some people just go get burgers, some people just go get fries, some people get both. We might like to ask, well, what's the probability that the customer is going to have both items in their order? What's the probability they'll have burger and fries? All right, so according to the addition rule, if we want to know the probability of burger or fries, at least one of those 2 things, we add up the component probabilities and then subtract off the probability of them both occurring. So 70% chance of having a burger plus that 60% chance of having fries minus that 45% chance of having both. We have to give back that 45% because it would have been double counted. That 45% would have been counted twice when we added up the burger with the fries. And that works out to be 85%. So, a related question, what's the probability that an order only has drinks? Well, you might be scratching your head because we don't have any information explicitly about drinks in the information here. We have something about burgers and fries, but if we put on our thinking cap, we know that the event, they just have drinks in the order, is really just the opposite of, burger or fries here. Burger or fries in probability means at least one of those two things, and so just drinks just means the opposite of having at least one of those two. So by the complement rule, that would be 1 minus the probability of burger or fries, or 15%. We can get that immediately without actually having any information directly about drinks. Kind of cool. If you want to see this with a Venn diagram, well, Venn diagrams don't have to be circles. You can come up with any shape that you want. Here, what I've done is I've drawn the sample space, kind of a very crude black rectangle, and then I've just cordoned off areas of the sample space corresponding to different events. So one thing that I did is I drew a blue rectangle to represent the 60% chance that an order has fries, and I've drawn a red fence to represent the 70% of orders that have burgers, not to scale necessarily. I know that 45% have both, so I have them overlapping with an area of 45%, and that allows me to fill in the rest of the pieces. If 45% have fries and burger, well, that means 25% must just have a burger with no fries. 15% must have fries but no burger for that to be add up to 60% and 70%. The space left over, no fries and no burger, meaning just drinks, there's my 15%. So very often you can get at the answers to some of these probability problems just visually with a Venn diagram, or if you want to flex your math muscles and use some of these rules of probability, go for it. The more practice you get, the better off you're going to be. Now here's the nice thing about this formula is that if A and B cannot occur simultaneously, a customer can't have exactly 2 and exactly 3 items in their cart. If we want to know the probability of one or the other, A or B, we straight up add the component probabilities. So when 2 events cannot occur at the same time, we say that they're mutually exclusive. And if that's the case, the probability of A or B is particularly simple. We straight up add those 2 probabilities together because the probability they both occur is 0. It's mutually exclusive. So when we do have mutually exclusive events, really easy. Let's go back to our stoplight example. The light's either going to be red, yellow, or green when we show up to it. And let's imagine that we have the following probabilities for each of those outcomes. So I want to know what's the probability that I'll be able to pass through the intersection when I show up to it. In other words, what's the probability the light's going to be green or yellow? Well, these 3 outcomes, red, green, and yellow, are mutually exclusive. The light's only going to be one color. So in this case, since I can't have green and yellow simultaneously, getting the probability that it's green or yellow, and therefore the probability I can pass through the light, works out to be the straight up addition of the 2 component probabilities, or 40%. Talking about dice and gambling, once again, the game of craps, what's the probability of rolling an even number on a die? Well, instinctually, you might say, well, that's 50%. Half the numbers on the die are even. That's the correct answer. But we can get there with the addition rule as well. To get an even number, it needs to be either a 2, a 4, or a 6. 2 or 4 or 6. It's only going to be one number once we roll it. So 2, 4, 6 are mutually exclusive events. That means if we want the probability of one or the other thing, we get to straight up add the component probabilities. We add 1 6 together 3 times, and it works out to be 50%. Now, we might have a different question about these 2 events. Instead of A or B, we might like to know, well, what's the probability that they both happen simultaneously? In fact, that was built into the addition rule. If we go back and look actually at what the probability was of getting A or B, we find that we have P A and B is kind of built into the rule for the addition rule, P A or B. So how do we get this P A and B in general? Well, that's where the multiplication rule comes in. And we're going to talk about the multiplication rule in much greater depth at a later time when we talk about conditional probability, because we actually need to know something about conditional probability to figure out the probability that 2 events occur. So there's two ways of writing out mathematically what the probability that both A and B occur. And these both use this notation you might not have seen before called the conditional probability notation. There's a vertical bar here separating A and B, vertical bar separating B and A. And the way that we read this, translate this back into English, is that this would be read the probability of A given B. In other words, we know event B occurred. With that knowledge, given that knowledge, what's the probability that A occurs? So to put this in a little bit of a context, we might want to know, well, what's the probability a shopper is going to have apples and bananas at checkout? Well, that would be the probability that they have bananas times the probability that, given bananas are in the cart, they have apples. And we can flip what A and B are. We still get the same formula out. We'll revisit this in a much greater depth at a later time here. What I do want to talk about right now is what happens if we deal with a set of independent events, like sequences of coin flips. The result on coin 1 is independent of the result on coin 2. Whether or not I win a game of gems right now doesn't influence what I'm going to be winning or losing on the game of gems in the future. Games of gems are independent. What if we're dealing with a set of independent events, and we'd like to know what's the probability that all of these events occur simultaneously? Like, what's the probability that when I flip 5 coins, all 5 are going to come up heads? What's the probability I'm going to lose a game of gems 10 times in a row? If that's the case, when I'm dealing with a set of independent events, and I want to know the probability that they all occur simultaneously, I straight up multiply the probabilities of those independent events. That works for 2 events, A and B. It works for a much larger collection of events, K different events. As long as they're all independent, I get to straight up multiply together those probabilities. So let's look at an example. Let's go and revisit Vegas and the pair of dice right here. And let's consider the case where we're going to roll 4 dice. I want to know what's the probability that I would roll 4 ones in a row on a die. So that's the probability that I get a 1 on the first roll, and 1 on the second roll, and 1 on the third roll, and 1 on the fourth roll. So I'm dealing with the case where die rolls are independent. 1 on the first, 1 on the second, 1 on the third, 1 on the fourth. Multiplication rule says I just straight up multiply those probabilities together. And so I multiply 1/6 by each other 4 times, getting 1/6 raised to the 4th power. Okay, well, what about the sequence 1, then 2, then 3, then 4? Well, it's going to work out to be the exact same probability because the probability of getting any particular number on any given roll is always going to be 1/6. If those die rolls are independent, then really no matter what sequence, 1, 2, 5, 6, etc., that I quote, if I'm quoting a sequence of length 4, all of those sequences are going to have a probability of 1/6 raised to the 4th power. Because each of those component rolls has a 1/6 chance of having the number specified. The multiplication rule for independent events says just straight up multiply all those component probabilities together and call it a day. All right, a little bit more fun of an example. So I have a bit of a sweet tooth. I can, go through a 2-pound bag of M&Ms probably in a day if I really tried. I really shouldn't because, they'll go straight to the hips or whatever. So let's do a probability question about M&Ms. So M&Ms don't have equal probabilities when it comes to colors. It's a little bit of a hidden secret these days about what fraction of M&Ms are red, yellow, blue, etc. So when I went and tried to look this up, these were the numbers that I decided to use. I decided to just kind of make them up just for illustration. So I'm saying that red, green, and blue are both 20% chance of occurring, orange and yellow 15%, brown 10%. So not the real probabilities, but something that we can work with. And let's imagine that during the manufacturing process, the colors get so mixed up, so well mixed, that for all intents and purposes, when you start drawing out those M&Ms from the bag, the colors of those M&Ms are independent of one another. So Good. The sequence of colors that we take out of a bag, we're going to consider as independent events, and we can use that multiplication rule to start answering questions about them. So, number one, I picked 2 candies out of the bag. I really should have my M&M prop right now. It'd be really a tasty treat. So what's the probability that they're both orange? Go Vols. All right, well, 2 events, we want to know the probability that they both occur simultaneously. The first orange, or the first candy we picked out was orange, and the second candy we picked out was orange. A and B. Independent events, multiply those 2 probabilities together. 15% chance of orange, 15% times 15% works out to be just a little bit above 2%. All right, well, let's kind of encroach into Skittles territory. What's the probability that we would pick out the colors in a rainbow order? Basically red, then orange, then yellow, then green, then blue, and then we'll have brown be the 6th and final M&M. So if all the colors are independent, pretty easy question. Those 6 different events, all independent, multiply the probabilities of the component probabilities. So probability the first one is red, 20%, times the probability the second one is orange, 15%, times the probability the third is yellow, 15%, times the probability the fourth M&M is green, times 0.2, fifth M&M is blue, times 0.2, and last and not least, brown at 10%. So multiplying those probabilities together, we get kind of like a mini miracle here. The probability of drawing those colors in a rainbow order would be 0.0015%. Hardly ever going to happen. But the surprising thing is, I could rearrange those orders. I could say, well, what's the probability of getting an orange, then a red, then a blue, then a green, then a brown, then a yellow? Any ordering of those 6 is going to have the same probability, because if I were to reorder the sequence of those colors, these 0.2s, these 0.15s, they would just appear in different places in that sequence. We'd still come out to be the same number here. So the probability of getting any sequence with all 6 colors is going to be that 0.0015%. All right, let's work on a little bit harder of a problem here. What's the probability of drawing at least 1 red M&M out of 5 candies? So let's say that we go through 5 candies. I want to know what's the probability that at least one of those 5 candies is red. Now I'm going to give you a hint. Almost always whenever I see the keyword or key phrase at least one, to me that's actually going to say, hey, you're going to want to use the complement rule here, because at least one is kind of a notoriously difficult quantity to calculate. Because in this context, at least, having at least 1 candy be red out of 5 means that there's exactly 1, or exactly 2, or exactly 3, or exactly 4, or exactly 5. That's a lot of different events to calculate the probability of. Notice that the opposite of at least 1 is exactly 0. So if we can get the probability of exactly 0 red M&Ms, we can just complement it. We can do 1 minus that probability to get our answer. So I'm going to immediately say this is 1 minus the probability that 0 out of 5 M&Ms are red. And I'm almost always going to do that. So if on the homework you're working through it and I throw a problem at you and I was like, oh, what's the probability that at least one of these things will happen? Very much typically easier to do the complement of that event. The opposite of at least 1 is exactly 0, and that makes it easy for us. All right, so for these red M&Ms, what do we know about them? Well, we know the probability that any particular M&M we draw out of the bag has a 20% chance of being red. So in order to have 0 out of those 5 M&Ms be red, that must mean that the sequence of colors must have been not red, and not red, and not red, and not red, and not red. 5 not reds all in a row. So at the risk of kind of adding too much detail right here, we can rewrite 0 out of 5 being red as the first is not red, and the second is not red, and dot, 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 dot. So all the way down to the 5th. Now, Because the colors we were assuming were independent of one another, the color I just got has no influence on the colors I'll see in the future. I know by the multiplication rule that I get to multiply together those component probabilities to get the probability that all 5 of these things occur simultaneously. So that's going to be the first, not red, times the probability the second, not red, times dot, 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 that the fifth is not red. Now make sure you do your order operations correctly. Make sure to do that product first, and then 1 minus that. But the probability of the first M&M not being red, well, that's a complement of red. That's going to be 80%. So 0.8 times 0.8 times 0.8 times 0.8 times 0.8. So that's going to be 1 minus 0.8 raised to the 5th power. And that's when we're going to have to shoot it over to R and say, hey, evaluate this expression for us. 1 minus 0.8 raised to the 5th power works out to be just about 67% here. So that's one thing that you'll find that I do a lot, especially when I'm doing business analytics problems. I don't carry too many decimal places with me. So technically this is 67.232%. But in business analytics, typically rounding to the nearest percent is going to be just fine. Remember, even estimating probabilities, it's kind of a ballpark sort of thing. We need lots of trials to get good accuracy. It's usually fine to just round to the nearest percent, maybe the first decimal if you're feeling a little bit generous. All right, well, how about the probability of drawing a red M&M and a yellow M&M? Well, in this case, I haven't specified red then yellow, so we need to split up this event, red and a yellow, into 2 component events. This is really asking what's the probability that you draw a red first, then a yellow, or you draw a yellow first, and then a red here. So there's 2 possible ways to make this event happen. The first red, second yellow, or vice versa. So red then yellow, easy enough probability to calculate. First one red is 20% times second one yellow, 15%. That works out to be 0.03. The opposite order, well, same end result here. First yellow would be 0.15, second red would be 0.2. Still get a 0.03 out. Add those 2 together by the addition rule. The probability of a red followed by a yellow or a yellow followed by a red, mutually exclusive, only one of those 2 things can happen. So we get to straight up add those 2 probabilities. We get a 0.03 plus 0.03, getting a 0.06 from that addition rule here. We'll come back to the example with non-independent events when we talk about conditional probability, but these sorts of problems would be useful when we're dealing with events that have some sort of relationship with one another. They're not independent. So if we're going to draw 2 cards out of a deck, well, those 2 cards aren't independent because the second card can't be the exact same card that the first card was dealt, as long as we're doing it without replacement here. So we'll revisit this at a later time. And I think the last remaining slides are just discussing the birthday problem and using the multiplication rule. Pretty long, pretty in-depth. Knock yourself out if that's kind of your thing. So that's going to be the end of Unit 1, kind of the overview of probability, some of the basic rules that help us out in analytics. And our next topic for Unit 2 is going to be how we can kind of use that frequentist view of probability to estimate probabilities by writing computer programs. Sometimes it's just too hard for us to count. Sometimes we can't enumerate the sample space. But we know how to estimate a probability, just conduct a whole bunch of trials, count up how many times our event of interest occurred in those trials, and then look at the ratio. So how can we write a computer program to basically conduct a trial for us, measure the outcome, and then come up with a really good estimate of the probability?